This will be a quick dive into Fourier series and discrete Fourier transform. A function f is said to be periodic if for some positive constant capital T, f at t plus capital T is equal to f at t for all t in R. What this means is that the real number line, when divided into chunks of length t, the function in each chunk will be identical. The least such capital T is called the period of f. It's clear that if t plus capital T is equal to f of t for all t, then f at t plus any positive integer multiple of capital T is also equal to f of t for all t. A periodic function is often called a signal. Let us now look at some examples. The first example is f at t equals sine of t. And the graph of this function should be familiar. So it looks like this, and in the negative direction looks like this, and it repeats itself every 2 pi. So the period of this function is 2 pi. Next, we have the function cosine 4t plus 3 sine t. This function has period 2 pi, and this function has period 2 pi over 4, and so this whole thing will repeat every 2 pi. And one can see from the graph, the period is indeed 2 pi. The third example is h of t, defined to be t when t is at least negative pi and less than pi, and everywhere else is given by this here. So at every point there is an integer multiple of 2 pi away from t is valued as the same as h of t. So if we plot this, let's take negative pi here, 0 here, and pi here. We have the function that is at the point negative pi, passes through 0, 0, and ends at pi, comma pi, but does not include this point. So the periodic nature of this function will look like this, and so on. So a couple of remarks. We normally use t for the input variable because periodic functions are normally defined over time domains. So t stands for time. And the function h is discontinuous at every odd multiple of pi. As we can see here, it is perfectly okay to study signals with certain discontinuities. It is known that under the Dirichlet conditions, which we'll see in the next slide, a signal f with period t can be represented by a convergent Fourier series. It is an infinite series given in this form, where the coefficients a0 and so on, and b1 and so on, are given by these integral formulas. One version of the Dirichlet conditions is as follows. For all real numbers ab, a less than b, the function f of t is bounded on the closed interval a comma b. And it has only a finite number of minima and maxima. And it has only finitely many discontinuities, each of which is a jump discontinuity. So here we have jump discontinuities at every odd multiple of pi. So let's look at the function h again, and we're going to compute the Fourier series representation by obtaining the coefficients. So we're going to work over the interval negative pi to pi, so that means t will be 2 pi, and the function will be given by t. And so the coefficients are given by these integrals, and we can work this out. Let's look at the first one here. So at pi, sine of k pi is 0, and this is cos k pi. And at negative pi, this sine is also 0. And this is cos negative k pi, which is the same as cos k pi. And so we have cos k pi over k squared minus cos k pi over k squared, and that's 0. And here we can use a similar reasoning. This will be 0 whether x is pi or negative pi. And this cosine, which depends on the parity of k, is either 1 or minus 1. And so it reduces to this. And so putting these all together, h of t is given by this series. And this is for all t at points that are not at the discontinuities. So we can sum up a finite number of terms of this series and see what the picture looks like. So up to capital N terms, h of t is given by this. And when capital N is 3, this is the picture here. And when it's 6, we have this picture. When capital N is 12, we have this picture. And as you can see, the bigger the n, the closer is the graph to the sawtooth that we saw for h.